grad studies at my alma mater, Unicamp. Then he did a postdoc in São Carlos, right after he finished his PhD. Then he went to Ohio, where in reality is where I first met him. He was working with Sergio there. And then he went to work with Dagoto, right, at Oak Ridge. And then he stayed in Oak Ridge. He stayed in Ohio from 2004 to 2007. And then in Oak Ridge in Tennessee, Knoxville, from 2007 to 2010. And since quite a few years ago, right? You are at USP. 2010. Oh, okay, yeah, 2010. He's at the Physics Institute at USP in São Paulo capital. And today he's going to talk to us about what's next in the Majorana saga.
Okay, George, thanks for the introduction. It's always a pleasure to talk to you guys in Uberlândia. I really liked, I would prefer to be there in person, and after we would go for a churrasco or something. I love the city. Hopefully we'll do that sometime.
Sure.
Okay, so today, as the title says, I'm putting this question of what's next in my Majorana saga. Before I think I'll interrupt my camera because my internet connection is kind of shaky. So I'll get the camera back online during the question. And actually I'm in presentation mode, so if you have any questions, just shout, because I cannot see you. Just unmute and ask questions. That's no problem. And so let's see what's this Majorana saga in condensed matter systems. I think that's this long search for Majorana that we have been going through, and I'd like to start to saying that what are we now at this point, and then I'll discuss something. A few comments on what's my view of what's next in terms of platforms, materials, or even topics that we can go from here. And then I'll give two examples here. Two works that we have been doing in our group with Rafael Teixeira, the PhD student in my group mostly. This is part of his master's work, and this is from his PhD work. But most of my group, we have been looking into these topics related to Majorana bound states in the condensed matter system. So there's many experts in the audience, so I'll just give an overview of where this Majorana saga started. And there's some controversy of whether this started in 2012 or if these search for these Majorana quasiparticles have a much longer history. And I think maybe you can date that to 1937, but I'm not going to do that. And I'll just put some landmarks here of where have we found these so-called Majoranas, right, in condensed matter systems. I think a good place to start is this 5.5 plateau in the fractional quantum Hall effect, where Murray and Reed famously proposed that this state could host non-Abelian anions, quasiparticles as excitations, which then would be Majoranas, and I think that's where the whole thing started. This is, I saw Andrew in the audience. This is something that we people who have worked with a two-channel Kondo effect also, looked at Majoranas there, but they're, they were kind of a construction. Even Juan Madalcena worked on this back in the day. And then now what I'm essentially starting my saga is 20 years ago, almost 20 years ago, when Alexei Kitaev published this very unpretentious paper in a rather obscure journal in 2001, where he proposed this idea of Majorana bound states on 1D P-wave superconductor, topological superconductor. And this is essentially the Kitaev model that every student that goes into this area has to learn. And I'm gonna, for people who are not in this area, I'm just gonna give a brief overview of what the Kitaev model is. We could be actually teaching that in solid states or quantum many-body courses, because it's very simple and has a lot of information there. So essentially, it's a tight binding chain, right? You have a chemical potential or on-site energy, and you have the hopping, but you also have this term here, which is a superconducting pairing between the electrons on neighboring sites. And this has a name nowadays. We call that the P-wave pairing term. And these are spinless fermions, right? So it's only one spin polarization if you want. And if we have an infinite chain, or you do periodic boundary conditions, you can write this Hamiltonian in the Bogoliubov-Desgen form, where k now is a good quantum number, and then the p wave appears here in the off-diagonal matrix elements in the BDG Hamiltonian with the sign of k of a. So this is different than the usual BCS case, where this term is usually a constant, doesn't depend on k. And here it actually goes to 0 for k equals 0. And that's the whole thing. So most of the field, and there are many theory papers written about this, is to find systems where you get a Bogoliubov-Desgen Hamiltonian with this structure, with this off-diagonal terms that go to 0 at k equals 0. And I'll give some other examples throughout the talk, but I think this is the important thing, right? So what's the search for Majoranas essentially boils down to finding BDG Hamiltonian with a structure similar to this one. And why is this nice? Well, we can diagonalize that. It's a two-band model, right? You have these two bands. It is in the BDG basis, right? So you have electron-like excitations, hole-like excitations, and these are the two bands. And you can plot them, say, in Mathematica or any software you want, and this is very structured for students to do. And one thing that you quickly learn, fiddling with this in Mathematica, is that for parameters, some set of parameters, there's a gap between the two bands, so they never touch, right? So this, in case where the absolute value of this mu is larger than, say, the bandwidth, 2t, this is gapped and is essentially an insulator, right? Just a regular case, of course, for a half-wave. Now, if mu equals exactly 2t, and if you look here at k equals pi, k times a equals pi, and you do the calculation, this thing goes to 0, right? And depending on whether you're crossing this can be at 0 here, or in this case where I'm putting delta equals to t and mu equals to 2t, the gap closes at plus or minus pi. But if you choose another delta, you can close it at 0. But the point is that the gap closes if you change the chemical potential. Now the gap reopens again if you, say, have mu equals 0 and delta equals t. So here I'm essentially putting mu equals 4t and then 2t and then 0. But this is a different phase than this one. And how can you see that? The way to see that is to rewrite your Kitaev model in terms of these Majorana operators. And again, this is a nice exercise for students, where essentially you have a representation of these fermionic operators in terms of these Majorana operators, which they obey the condition that the gamma dagger equals to itself. So this stems from the original Majorana paper in quantum field theory, where he found real solutions for direct equations, and this is essentially a different basis, if you wish. So the Hamiltonian is essentially the same. You didn't do anything. This is an exact transformation, but gives you an essence of where that topological phase transition is telling you in terms of these excitations. So what happens is that if you have the first case where you have a trivial gapped phase, and this example where t equals 0 falls into that category, this is essentially tells you that you're dealing with an insulator. So you have these two Majorana bound states closely bound to each other, and here, so you have t equals 0 equals delta, so you only have this term. So you only have these B-type Majorana coupled to this A-type Majorana, and they are bound together. So this is just a trivial state. And you have the other one where I mentioned where I had mu equals 0 and t equals delta different than 0. In this case, this term goes to 0. This one actually survives, and this one goes to 0. And you have this sum in your tight binding chain starting at 1. But the first term is a B-type Majorana coupled to the A-type Majorana in the next site. So you have these, these bonds, I say, between B and A, but they leave this A and this B standing right at the edge of the system. So this is a topological phase in the sense that you have these these Majorana modes just sitting there at the end of the chain. And to give an analogy, if you look at this transformation here, essentially you can
Hey, Luis, I think your sound is breaking down.
Yes, yeah. I think he has some problem.
Yeah, he's disconnected. Mm-hmm. Yeah, he warned us that he was having problems with his. There he is. He's back. He's gone.
Yeah.
Well,
he will be back.
He has a backup system there that he's gonna use his cell phone as a hotspot, so we can try to tell some jokes while he's away, or we just wait.
I hope he's not together with Majorana. Otherwise, we will not be able.
we will never find him again. Yeah. Or maybe he's in Argentina together with Majorana. Like everybody who disappears in the world, sooner or later they end up in Argentina.
If I contact with a different channel. Let me see.
Do you have his cell phone?
Mm-hmm.
His cell phone number, so if you could call him and see, well, if you call, you're gonna be interfering with his attempt to connect.
I'm having. Hold on. Hold on, people. He must be probably trying to reconnect.
So guys, while we wait, I'm curious, did you get vaccinated yet?
Not yet, and nobody that who I know has been vaccinated yet. I don't know about you, Watson. Do you know anyone?
No.
No.
No. I know some people that have been vaccinated, but they are older. So.
And Sergio, have you?
Actually, no. You know,
No?
here in Europe is between AstraZeneca causing blood clots and just not having enough vaccines. They're going slow. I mean, they've started. There are already vaccination centers, but they haven't reached my age group yet.
Here in New Zealand, apparently they started the 65 people, 65 to 69. I think they are at this range right now.
No, here they're still in the, I don't know exactly, but certainly it hasn't. I haven't been called. Here you get a text message basically telling you to go register, and it hasn't come.
It's organized. Yeah. Here
actually very well organized. Yes, amazingly well organized.
Here in Brazil, they are well organized too. The federal government is waiting everybody to die, and then they're gonna sell the vaccines to Europe. They're gonna sell the vaccines they already bought. They're gonna sell it double price to Europe.
Double, that's right.
Yeah, they're gonna make a buck.
Why not? I guess.
Yeah. Who knows?
Oh, well.
Luis is coming back.
Luis is back.
Well, he's back.
He's back. Great.
Let me find you here. So
I was talking to myself here.
Okay.
So you have finished already your talk?
Yes. Oh, no, almost halfway through the talk. So where did you guys miss me?
Oh, I think you were explaining the trivial and topological phase in these simple Kitaev chains.
Okay. No wires then. I think I was here.
No wires yet.
Okay. Yeah. So I'm going to speed up a little bit. All right. Sorry about that.
No problem.
Okay. So I was here, right?
Yes, that's it.
Did I talk about the glass half full?
I think you were about to talk about that.
I was curious whether that was coffee or tea or what was it?
Yeah, the thing, maybe I don't know. I stole these pictures from Leo Kuenhoven. Maybe it's juice.
Maybe it's juice.
Grape juice.
So okay, so yeah, I was essentially saying that you can tell the difference between the topological and trivial because you have these hanging Majorana modes at the end of the wires, and of course the question is whether you can realize this experimental, right? So it's a rather simple model, and yeah, let me get rid of my camera here before my internet starts to go bust again. Okay, and then yeah, that was a big question, and of course there's these two papers that came out in the same edition of PRL, back to back, where both groups, one from Maryland essentially, and the other from Berlin and Europe in general, they proposed that you could realize the Kitaev model in 1D nanowires with two extra ingredients: spin orbit coupling and a magnetic field. And yeah, I'm not going to go through that. These are very nice plots that my student Lucas Baldo made, and he's defending his master's dissertation tomorrow. And the idea here is that if you are in the right parameters of magnetic field and you have a spin orbit and the Zeeman coupling, you open a gap in the system, and you actually can have a situation where if you have, in addition, S-wave, real S-wave induced superconductivity, you introduce in the effective Hamiltonian, the effective low energy in Hamiltonian, it has a P-wave character that you have in a Kitaev. So again, this is the game of finding P-wave superconductivity, or at least trying to produce right in the BDG Hamiltonian and have these off-diagonal terms with this k with this k dependence. So it goes to zero as k goes to zero. And then the experimentalists, of course, jumped into it. And in 2012, we saw this, this paper out of Leo Cohen-Hoven's group in Delft, making a big splash at the March meeting, room packed of people, people sitting on the floor, and he announced, that these zero bias peaks were signatures, or at the time, that's what was thought, that these were signatures of these Majorana modes at the ends of these wires for a range of magnetic field that was in principle compatible with the theory. And other experiments follow where they saw these zero bias peaks as well. But even from the beginning, there were many comments saying that there could be other effects leading to zero bias peaks. One of them would be, of course, condo physics going on that would appear at zero bias. Others would be disorder effects. This could be not Majoranas, but Majorana bound states who turn to have energies very close to zero. And then for the good part of these last 9 years, the experiments evolve, the materials evolve, they start encapsulating these wires with the superconductors, trying to get better data to make sure that you would get something close to what would be a signature for a Majorana bound state. And then there are many different experiments. And in 2018, they published this paper in Nature, where they said, okay, here we have a very good evidence that these things are Majoranas, because now the conductance is quantized. And it's quantized at a plateau that is 2e squared over h for a long range of parameters, where they say, okay, now this is a very good, if not a smoking gun signature of what you would expect for the Majoranas, with much better data than what they had before. The problem is that there are many points that were later observed in the data from this paper, and I'm going to point out a few of them. And this paper eventually got retracted, and that was, a big moment, I think, in the story of this Majorana saga, where now they published this, or they uploaded this paper on arXiv in January, the end of January, essentially retracting this paper and redrawing some conclusions from their data. So let me summarize, give you a few examples of what's going on. So this is figure 2 of the original paper, and this is figure 3 in the retracted paper in the arXiv, and this has since been published. Since I got this figure. And one thing that you will immediately notice is that there is something missing here. in the nature. So this whole section and in others as well, like this big one here, but this one is telling, right? Because if the argument is that, okay, we got this the IDV conductance as a function of a tunnel gate voltage, essentially is a gate voltage, they squeeze the edge of the wire and make it a barrier to the lead larger or smaller, and this is independent of this tunnel gate voltage and stays always at 1. This is not really the case, because you have a huge drop here, a huge drop. You have this blue island here, and this actually was pointed out by Sergei Frolov, who was in fact a former not sure if he's a student or a postdoc in the Delft group, and a co-author in the original 2012 paper. And they actually had access to the raw data from the group, and they found that these things are missing, and this indicates that you have a jump in the conductance and could be due to improved charge impurities in the sample, right? And okay, that was raised eyebrows. And then also in the retracted paper, they correct a calibration error in one of the lock-ins, and what they thought was 1 is actually 1.1 or 1.08. And now these oscillations that you thought, okay, this is all about 1, they're not. It does tell a different story here, right? So this point, even outside the error bars, is more like 1.2, almost 1.15 maybe. So this figure tells a much different story than this one. And it seems, and Dasarma is one of the co-authors in the original paper, and he actually did calculations disproving some of the conclusions. And this is, say, one example from the retracted paper, where they see conductance way above 1, outside the error bars. And in their group in Maryland, they produce simulations where they see very similar things with no topological phase, just adding disorder to the sample. So this was one of the arguments that you definitely see some zero bias peaks coming in, but you cannot tell that they are Majoranas from this data alone. And of course, this figure came out on Twitter before coming out on Archive, which is an interesting sociological consequence of this whole thing. A lot of the discussions is taking place on Twitter and rather than in the Archive now. So even I went to the social media, and actually I gave a talk about this paper in our group meetings, and then I decided to record a video and post it on YouTube, and it already got maybe 750 people watching it, and I was really surprised when an email message from Shankar Dasarma himself popped up in my mailbox, and he said that he watched the video had a few comments, but generally he liked the way that it was presented and so on. So, tell me that people are really paying attention to social media, even in physics discussions. And of course, in the last March meeting, for those of you who attended, it was all online, so didn't have to travel this year. There are several talks where they discuss this, let me just check if I'm still online. Yeah, okay, right. And one of them was, of course, Leo Kornhoven himself. He gave a talk, and one of the things he showed is a diagram like this, where every dot here is like a zero bias peaks. So if you pick and choose which zero bias peaks you like most from a range of parameters like this, you can easily cherry pick. And if you have some sort of confirmation bias, okay, we want to look for robust zero bias peaks, you might find one in this whole data. But it's really hard to show that, this whole thing, your topological phase diagram looks like this, right? And he ended his talk saying, okay, where do we stand? Of course, they see these zero bias peaks everywhere, but they have to check for a huge parameter space. And the Sarma gave a talk saying, okay, essentially saying that you cannot trust any of the data from any of the experiments on nanowires because the disorder in the samples is just too high. Essentially, he said in so many terms. Of course, Charlie Marcus gave a talk on these other systems where they have these full shell nanowires, and they get these essentially these parameters that come from little Park's destructive phase, where you would see zero bias peaks in one of these lobes. And yeah, this was a science paper, I think, last year or so. And then there came a talk from George Katsaros at the last day of the March meeting, where he showed data from experiments with full shell nanowires and saying that he found many zero bias peaks, but when he went to look closer, none of them were Majoranas. They were all Andreev bound states. And there was even a comment in this session saying that, you should be more forcefully saying that what you see is not Majorana bound states, particularly in view of the claims coming out of Copenhagen. And so, there's a lot of skepticism. There was before, but now it went to ranges that you cannot, it's not even for an experimentalist now to come out and say, okay, this is a robust view of or a signature for these Majorana peaks in the nanowires. So the point is, these experiments in nanowires are now challenging, and it's going to be a long way before we have the materials with low enough disorder and protocols for double check consistency in the data, saying that those signatures are Majorana. And actually, you cannot do that without some sort of non-local experiments, and that's becoming clear. So the road, again, with nanowires is very challenging, and people have been asking, okay, can we look elsewhere? And this is one of the things I'd like to tell you a little bit more about. What kind of other kinds of systems can we look? And I'll give you an example of another, say, competitor platform, if you wish, which has gained some traction a few years back, and actually since the nanowires were taking off, kind of got downgraded, but I think they still deserve a chance, since you have a very nice local way to probe the Majoranas in situ and maybe manipulate these systems, which is magnetic chains on superconducting surfaces. And here, the game is pretty much the same as we had seen with the nanowires, is to come up with a BDG Hamiltonian where you have some sort of P-wave superconductivity. And the way you do that is, if you have a magnetic system on a superconducting surface, you have both coupling between these spins and this induced superconductivity in these spin degrees of freedom. And if you write the low energy Hamiltonian for that, you end up with a BDG Hamiltonian that can have a P-wave pairing, depending on this beta parameter, which is actually a measure of a spiral order along the chain. Okay, so this is the original paper, where spiral order along the chain is an important component in obtaining the so-called P-wave pairing in this system. Now, it came another proposal, and actually an experiment from the Princeton group by Yazdani, where they had not a helical spin chain, but a ferromagnetic one in the presence of a superconductor with strong spin-orbit coupling, and here spin-orbit plays the role of this spiral angle, and in the presence of spin-orbit coupling, you will get a Hamiltonian like this, and that's where the theory is, and you may end up with these Majorana bound state here, and that's what they showed in the STM images, and the STS also curves showing that if you put the STM here at 3, you see nothing, you just do these Shiba bands, but if you put at 1, or not even 2, but at 1, you get these Majorana quasiparticles. And of course, this has improved to different systems where they try to improve this data set, because there were also criticisms on this experiment where they put these iron clusters at the edge of a topological insulator on a superconducting surface. And actually, our proposal is more along these lines. And actually, this came out after our first paper on the subject, which was the result of the work by Rafael during his master's, where in our model we have essentially the same ingredients. We have these magnetic chain on top of a 2D topological insulator on a honeycomb lattice, which is very similar to the one that Kyle showed us 2 weeks ago. And now you put that on top of a superconductor. So you have essentially a K-mill kind of model with superconductivity and with these magnetic impurities, where you allow that for a spiral angle and some helical or some spin helix, if you want, going around the chain. So this is the magnetic impurities here we treated in a single particle limit. So we just can think that as the magnetization coming from a local Zeeman term. So Zeeman, this is one of the important parameters here in our phase diagram, which is this. It controls the intensity of the magnetic moment on each of these atoms, and also the chemical potential, the overall chemical potential of the K-Melee model. So if you tune these two parameters, you want to find a region where you might have a topological phase. And one important ingredient here is that the gap that comes out of the superconductor is calculated for each point in a self-consistent way, right? So it's not just a constant, not just a parameter, but it depends on the density states of the system, of the topological insulator underneath it, right? And so essentially you calculate this order parameter in a self-consistent manner, recalculating the order parameter until you get convergence. So we would not only depend on the parameters of the system, but will depend locally on the position of the site for each magnetic atom. So this is an important point. And to probe whether this is in a topological phase or not, we can calculate a chair number, a Majorana number, for the system with periodic boundary conditions, and then we can build phase diagrams like this. So this is for a chain in the middle of this topological insulator. And we do find a phase, which is depicted here in gray, where, say, as a function of the Zeeman term or the magnetic field for a fixed mu, there's a closing of the gap at one point, and you have a topological region here in gray, and then the gap reopens, and this is for periodic boundary conditions. And then if you do the calculation with open boundary conditions, you see these zero bias states, or these states near zero, and as you increase the length of the magnetic chain, the amplitude of these oscillations decrease exponentially, indicating that these states are becoming exponentially localized at the edges of the chain. So you have, Majorana modes, essentially. Now, the point is that we had is that even if you have helical order or if you don't have helical order, you still have these Majorana. So the spin orbit coupling within the topological insulator also plays a role. But more importantly, if you drive or if you put this chain at the edge of the topological insulator, then the phase is changing. You actually get a much broader topological phase if you have the chains placed at the edge. So not only the topological insulator plays the role of providing the spin-orbit coupling that you need to get the Majoranas even in the absence of the helical form, but also it improves the edge states of the topological insulator to play a role in improving the range of the topological phase that you have that you can access. Now, we did some studies and try to understand what these phase boundaries were like, and for one, that placing the chain closer to the boundary or exactly at the boundary actually changes this transition, the earlier transition, the first closing of the gap, and we found that this is related or very close to the case of a Shiba band merging together and closing the gap. That's where the gap closing comes from. And the other thing that we did is, okay, even if you have the helical order or the spiral order along the chain, you still have these topological phases, but now the things are not so simple. You have these crossings of the phase boundaries, and you have some points where you have no topological phase as a function of field. So this is a very rich system, but it is robust that you don't have to. This works whether or not you have this helical structure along the chain. And one other thing is that when you move the magnetic chains towards the edge, your Majorana states get much better. How so? Well, here we're plotting the spectrum for the same length in the chain, but just moving the chain to the edge. And here the amplitude of these oscillations actually decrease quite a bit. Actually, they decrease to the point where you cannot tell them one apart. And this is an effect of the coupling to the edge states, that they renormalize the superconducting gap, actually increases it, and then the quality of the Majoranas get much better. And we say quality in a way that we can measure it. We calculate this thing called the Majorana polarization, which is 0 if you have a perfect Majorana, zero energy Majorana state with an equal components of electrons and holes into it, right? That's what defines your, true to God Majorana state, and not an Andreev bound state, which might be more of an electron like or hole like character. So whenever this thing is 1, you're talking about a true Majorana bound state, and when it's half or something in between, 1 is more like a Andreev bound state. So if your chain is in the middle of the topological insulator and you calculate this quantity as a function of the Zeeman term, when you enter and exit the topological phase, of course, if you're away from topological phase, this thing goes to 0. But even in the middle of the topological phase, this is not so good. I mean, you might have 50% Majorana polarization. You might get better if you increase the size of the chain from 20 to 60, but you never reach 1. Now, if you move this thing to the edge, you get almost 100% Majorana polarization right at that 20 side chain. So the effect of these edge states from the 2D topological insulator is a real gain in terms of quality to the Majorana bound states. So I think this is a system that you can, in principle, engineer, and that's one of the results that I showed in that experiment. Here they're doing something a little bit different than what we proposed, but they do see signatures of these zero bias states that we are proposing here. How much time do I get, Edson?
I think George is controlling the time.
Yeah, you have 10 more minutes.
10 nanometers. Okay, that's enough.
Okay.
All right, so this is one of the directions that we're going, to try to see Majorana states, not only quantum wires, these nanowires, even though we have some work on those. There are some other students working on 2D vortices, for instance, like Bruna, who's spending some time with Nancy in Copenhagen right now. And the other thing is more speculative, which is this issue of parafermions, which are cousins of the Majoranas. So let me see if Xavier is here. Maybe he's not. Okay, but he would like this part. So the thing is that, if you talk to people from statistical mechanics and talk about, the Kitaev chain and Majorana and say, well, this is known for a long time. Essentially, if you look at the Ising model, just, an Ising model like this one with a transverse field, the Kitaev chain can be written as an Ising model, like just regular Ising spins. And how you do that? Well, essentially, what you have, if you write an Ising model like that, and you define these Majorana operators like this as these products of Pauli matrices, say up to at site J is a Z Pauli matrix sigma J, and then a product from K equals 1 to J minus 1, multiplying it. This essentially have the properties that you want for Majoranas. The dagger of this guy is itself, and you can define another one, a B Majorana, which also is the dagger of it is itself, and they have all the anti-commutator properties that you would expect in Majorana operators. And in fact, if you do this transformation, you write this Ising model precisely as a Kitaev chain of Majoranas, right? In the limit of delta equals t equals 2j and mu equals 0, you get precisely what I showed you in one of the first slides. And now the tricky part is to get a fermionic model out of it, because now you have to do some sort of a reverse Jordan-Wigner transformation and write these fermionic operators in terms of these matrices, inverts that, and write the matrices in terms of these fermionic operators, and then write a fermionic model. And then there's where P-wave superconductivity and all that appears. So from the point of view of the Ising model, this is simple, but if you were looking for a fermionic model, this can get really complicated really easy. Okay, so that's is known as, it's been around from, with a simple Jordan-Wigner transformation, you can do this transformation and get the Majoranas. But the interesting thing is that you can generalize these Ising type of chains to higher dimensions, if you will. So instead of a spin 1/2 Ising model, you can think of a generalization for an arbitrary n, say n equals 3 or n equals 4, where you have this now, instead of a 2-state spin, you have an n-state spin, right? And the eigenvalues of these spin matrices would be then 1 omega squared with omega equals e to the 2 pi I over n. So if n is 2, this is -1, so you get only 1 and -1. That's the eigenvalues of the usually sigma z Pauli matrices. But you might define that these generalized matrices called, say, Sj and Sj1, which have all this structure here, right? And there's some rules in how you would have to write your Ising Hamiltonian and how you get these Ising coupling. Of course, the Hamiltonian has to be Hermitian, and it has to have Zn symmetry the same way that Pauli matrices have Z2 symmetry. So one interesting case, and these usually are called clock models or Potts models where you have, the clock coming from a structure like this, right? So if this is 4, for instance, it's like a 90-degree rotation. So you have 12 o'clock, and you have 3 o'clock, 6 o'clock, and 9 o'clock, and this keeps returning. So it's like a 4-hour clock in a sense, right? And this actually has other implications in the sense that you might have to construct topological qubits who can do more than the usual Majorana qubits, because the parity here is a more complex thing. It doesn't only have 2 eigenvalues; it has more. So you have more ways to rotate your gates if you wish. So, but that's one of the motivations. So let me give you an example of a 4-state chiral clock model where you put all this algebra here and you build these generalizations of the sigma z and sigma x matrices, what I call here sigma 4 and tau 4, and they obey these properties, these relations. One of them is that sigma 4 to the 4th power is the unitary matrix in 4x4. And now sigma dagger is not equal to itself, but rather it's equal to itself times 3 times. So this is, you can see that the generalization from the Majorana to a parafermion right from here. Now you can go ahead and write an Ising model out of these matrices here. And of course, this has to be Hermitian, and your coefficients have to obey this. But the important thing is that the Hamiltonian is Z4 symmetric. So the same way that the Zeeman term is Z2 symmetric, the Ising term is Z2 symmetric. So if you multiply your matrices by -1, the model itself goes back to itself. This one is Z4 symmetric. So you can multiply it by I, or -1 or -I, and you get the thing going back to itself. So the parafermions, or the Z4 parafermions, are defined in the same way as we define the Majoranas in terms of these extra matrices, right? So you can go ahead and do, and then you define these the Z4 Majoranas, or what you call the Z4 parafermions, and they have these nice properties that mirror those properties of these matrices. So, for instance, they are not, the dagger of these parafermions are not equal to itself, but is equal to the n -1 power. So phi j dagger equals phi j cube, and etc. They have these also anionic exchange statistics. It's much more complicated than the Majorana case, because now there's some chirality going on. There's a preferential way of constructing this in terms of where you are in the chain. So the operators coming before you or after you, they do matter in terms of the exchange statistics. But you can construct that. You can construct an Ising model out of these parafermions, and it looks very, very much like a Kitaev chain. But now these things are not Majoranas, but they are these parafermionic modes. And in fact, notice that you have these hanging parafermionic modes on the edges of the Ising chain, like this chi1, right? So you have the connections between this psi and this chi. So these are the equivalents of your A and B Majoranas. Here, chi1 doesn't enter in the Hamiltonian, nor psi L. So these are 2 hanging modes, just like the Majorana edge modes in the Kitaev chain. Now the question is, can we do a reverse Jordan-Wigner transformation and write these things in terms of fermionic operators to try to get an electronic system behave like that? And this is a very tough question. This is the question that was a project for Rafael, and we learned that you can. Actually, I forgot to put the reference here, but these guys from Thomas Schmidt group in Luxembourg, they did it in 2018, and they came out with a fermionic model that actually has these Z4 edge parafermions. And I'm not going to go into details of how you do it, but let me tell you the basic ingredients, what you get. You get not only the p-wave pairing that you get for Majoranas, but you get some ugly and rather exotic interaction terms, like an electron-electron interbody interaction, a two-body one, and you even have two-body p-wave pairing terms, and even three-body interacting terms that involve 4 or maybe 6 fermionic operators each. So it is a very complicated, strong correlated model, but still there. I mean, if in the case you have well-defined phases, just like you have in the Kitaev chain, where you can find these parafermionic modes. So one of the phase diagrams here you can think of is in terms of these 3 parameters, right? So the hopping, the superconducting pairing, one body, and this overall interacting term W. So if you have W equals delta equals 0, you just get this term as a trivial maple, that's tight binding chain. If you have W equals 0, this is just the Kitaev chain, but with spin. So we have 2 Kitaev chains, one for each spin, if you want. And it's a gap system with 2 Majorana modes, with 2 Z2 Majorana phases. Now, what's interesting is that if you have T equals delta equals W, you go back to one of those Ising chain kind of models with the Z4 parafermions hanging. And that's the thing that we try to study with DMRG. We can go into these different phases and calculate the gap for the strongly interacting chain, and see that, yeah, indeed we have phase transitions between these 3 corners in this phase diagram here. And the question is, okay, what if you don't know the gap, right? Can you probe whether you have a parafermion here or not on some other way? And in fact, you can use a quantum dot as a parafermion detector. And the idea here is very closely related to this idea of using quantum dots as Majorana detectors that came from this paper by Liu and Baranger. And also Edson has played a big role on this, where had this idea since 2014. We even worked on that, getting the interacting case a year later. And the idea here is pretty much the same, right? So you attach the quantum dot to the system and try to look for local properties in the dot that would indicate that you are in the parafermion phase here, the Z4 phase. And in fact, if you calculate the local density of states at 0 frequency with the MRG, and you plot this as a function of the parameters, a very similar phase diagram as the one that you get from the gap emerges. And this indicates that here you are in the Z4. So this circle here is this blue curve here. Here you are in a trio case, so you have nothing in the local density of states in the dot. And in the triangle, you can even distinguish the 2 topological phases, whether you have 2 Majoranas or you have the Z4 parafermion in there. So this is interesting because this is robust. It also relates to the charge of the dot. It's not here is a little bit more subtle. But if you could measure the charge of the dot on each of these 3 phases, you would find tiny differences, maybe 10%, of whether you are in one of these 2 topological phases or you are in the trivial phase. So this is the difference between the charge at the trivial phase and the charge at the topological phases. And you can even even from the charge, now is a much harder task, but you could distinguish of whether you are in the Z4 or in the 2Z2 phase. So with that, I'd like to just present you the group members, and the works that I told you about were performed by Rafael for the most part, and many other of the people in this picture are working on Majorana related things. So this is something that we are following very closely, and I'd like to thank you for your attention.
Thank you, Luis. So now this paper is open for this paper. Sorry, this the seminar is open for questions.
I have one question. I have many, but I will by now keep most one. So when you show actually you mimic the magnetic chain on top of topological insulator, where you have the honeycomb chain. Mm-hmm. Okay, to make your impurity, I think, as far as I understood, you applied like an on-site magnetic field.
Yeah.
So this is essentially like an staggered field. So
yeah.
every site you change the direction of the field. So this is your idea, is just to mimic the impurity, or you are thinking about constructing such a realistic system using this magnetic field? In that case, I think it's kind of hard to get this.
So the magnetic field is uniform. So the VZ here doesn't depend on site position, right? Mm-hmm. So the magnetic moment of the chain is uniform. What happens is that the direction of the magnetization changes from site to field. That's what we're controlling. I mean, so this is mimicking some internal mechanism that comes from coupling between the chains that would produce this spiral order along the chain. But the magnetic field, the Zeeman, would be the same for all atoms in the chain. But even if you have, but I think that one of the important things here is that even if you have, a ferromagnetic chain, and this is the case here, the thing works pretty much the same. It's even better, actually. The phase diagram is actually more well behaved. So, just ferromagnetic aligned chain, and you apply a Zeeman, that you increase the magnetic moment as the Zeeman increases. So that's the plot here. So the higher the magnetic moment, the lower the threshold in chemical potential you have for going into the topological world.
Okay, so what makes the direction of the magnetic moment to change side by side? Is the northern direction?
Could be like then you have to model the chain itself, right? Of whether you have Dialogisk Moria or something else going on there, and you might have a torque between the spins. We didn't include that in our model. We just put this as a phenomenological, say, parameter that is that spiral angle. So that angle is something that we put by hand, if you want.
Okay, just to finish my question. So when you move your chain toward the edge of the material, of the sample, so why is better? Just because the denser state of an underlying material, of the host material, is more pronounced at the edge, right?
Yes.
So the coupling is more efficient, more effective.
Yeah. So I think that this is definitely an important factor, that now you have an edge state sitting there that will, when you recalculate the induced superconducting order parameter, it will increase. So you can see here in these plots that the gap, the whole gap, the distance between the lower band and the top band in the topological phase, they're increasing just by moving it, and that's an effect of the edge state. So the topological edge state plays a role here in renormalizing the gap, but it also extends the topological region. So it's not only the gap that increases, but the topological region increases too. So it actually makes it a more robust coupling to these Shiba bands in a sense, so they collapse earlier in magnetic field. So there are two effects going on here that are a result of this coupling to these helical edge states.
Okay, thank you. I have any other, but I can talk later, or maybe tomorrow.
More questions? I have two questions. It appears that you read carefully the retraction paper. Do they mention what kind of disorder they are talking about and how severe this disorder is, and what processing would be, if any processing, difference in annealing, I don't know, things that that experimentalists do when they try to get rid of disorder?
Yeah, that's a very good question. So if you ask the Sarman, and his talk at the March meeting, he talked a lot about that. So in his papers, they do several kinds of disorder, like the chemical potential changing randomly along the wire, right? For instance, interface disorder, things, anything that will change that uniform, nice Kitaev model that we have, will produce accumulation maybe of Majorana Bound States at some region, and that would be picked up in the conductance. So it could be that, it could be charge impurities, like charge impurities definitely are there because of that huge jump in the conductance, let me show you here. Like this thing here, this is a charge, an extra charge that appeared there, that at some point it start to, as you change the gate voltage and you were squeezing, your potentials there, it essentially, you uncover that, and that make the thing jump. So there are lots of things. So the Sarma is, during one of the talks by some people in Delft, he actually made, the guy showed these beautiful, interfaces between the superconductor layer, the shell and the nanowire, very nice, and said, oh yeah, this is almost perfect. And then Sarma in the comments, he said, yeah, you think those are nice. If you translate that into energy, this is a huge disorder window, right, in terms of strength and energy. So one thing that was clear is that they need to do something similar to what was done to find the fractional quantum Hall effect. So it's not, a factor of 2 or 4. It has to be orders of magnitude better quality of the materials in order for you to see the real thing. That's the point that that Sarma was making. So I asked him this question of whether you would need Lauren, Pfeiffer, and West kind of quality in their samples, like you did with gallium arsenide back in the day, to actually see the fractional plateaus with the nanowires, and said, yeah, it's pretty much very, very similar. Said that back and then you also needed higher magnetic fields that you might not need now. So, I mean, it's doable.
It's doable, okay.
And, they would have to improve their growth procedures a lot.
Okay. And if no one has another question, in the system that you showed, very nice, by the way, with the superconductor, the Kahn-Meillet model, is it just the regular Kahn-Meillet model with intrinsic spin orbit, right? Yes. No Rashba and in this, yeah.
You could include Rashba, and it just makes the calculation harder.
Okay. Yeah. Sure. but it's a simple K melee, so any hexagonal lattice that that has that would suffice.
Yeah, like the one Kai was showing 2 weeks ago.
Yeah, sure. Anyone? Any questions?
Luis, all this
yes, I was waiting, guys. May I?
Sure.
Go ahead.
So now I was just getting directions from Nancy because she connected to your talk, but only with the audio, not with the mic, and apparently you cannot reverse that decision. So I'm her voice now. And the question is, Nancy, what are the conditions for the parafermion model? A material. What material do you have in mind for the parafermion?
No, yeah, very. I don't have any idea to be honest.
Let me actually make a comment that there was a paper I saw in the archive by Philip Kim that basically claims that graphene can be used for parafermions. I think it's a double layer graphene, and they put it next to a superconductor. I don't remember the details.
It could be. I'll look into it. But okay, so what I know is there are a few proposals. Well, first, the most promising are fractional quantum Hall states, right? Where you would presume that if you have the right samples, those excitations would be parafermions, like because of the fractionalization of the electrons there. Now, in condensed matter, multi-layer graphene, now they're talking about tri-layer magic angle graphene, right? So and multi-layer magic angle graphene, and if you would be in a March meeting and say, okay, everybody's working on that, this is going to be solve mankind's problems, and maybe it could be. I have to take a look at that paper by Philip Kim. But the thing is interactions, and there's a couple papers by Daniel Loss's group where they try to have I think nanotubes, regular nanotubes, or maybe carbon nanotubes, a bundle of nanotubes where if you do the bosonization and low energy theory, you might get a situation where you have the right symmetry for the appearance of these parafermions. But at some point, you have to have a mechanism that you have things like these three-body interactions. Even in those cases, there would be some kind of backscattering that will turn out to be that it will be resonant when you have three-body interactions effectively. And you need those, otherwise you just get a collection of Majoranas, right? So here in this Hamiltonian, it essentially tells you the story. So if you have only the first two terms, just P-wave pairing, you get just a bunch of Majoranas. So in order to get these Majoranas to form a parafermion in a non-trivial way, you need electron-electron interaction, but you need these three-body terms. Now, how to design those in the material, I have no idea. Maybe you can do that in graphene, but it's like, as I said, Daniel Loss has these ideas of using bundles of nanowires to do that, to engineer that, but it's really...
Luis, Nancy is asking whether you can induce them with electron phonon interactions.
Yeah, so you said. Good question. Good question. You would have to engineer an electron. So the scattering of 3 electrons mediated through phonons, where this would be a relevant, scattering. Maybe you could. Maybe there's some selection rules in multi-layer graphene that allow for that. But three-body interactions.
No, go ahead. Sorry.
Three-body interactions you find in QCD or something, like those weird vertex of high energy physics. In condensed matter is much harder.
I was gonna ask. So in the Hamiltonian, they all have the same coupling constant. That's also like fine tuning.
Yeah, well,
That
that's in our model we put them all together, so we have just 3 parameters for the phase diagram. I think if you put the different strengths, you might have topological regions in this, 5-dimensional phase diagram.
Multi-dimensional,
yeah.
Right.
Yeah.
Okay.
But
okay.
So they don't need to have the same strength. Yeah.
Okay. I actually, Luis, I had a question of my own, if I may, which is here in Copenhagen, the Charlie Marcus and company are playing, and they're not the only ones, but they have this material which is like a 2D. Now I forget. It's aluminum, and then it's gallium arsenide, I think, or indium arsenide. That's it. It's aluminum, indium arsenide, and some superconductor. Or the aluminum is the superconductor. Indium arsenide is the high spin orbit, and they have something at the bottom. Forgotten now, but
that's a heterogeneous structure.
It is, but see, now you have everything is covered. You can do lithography on it and can make wires and so on. So they published several papers, Science and PRLs and so on, where they do transmons and so on with that technology. And and I wonder whether, and presumably it is more stable than the nanowires that they have been playing around, right?
I saw those transmon papers, but they never claim it's Majoranas, right?
No. They're not.
It's more like Josephson junctions kind of.
Exactly. I think that, well, as I said, they have transmons, right? They're making transmons with that. Never mind Majoranas, they're going the safe route, basically, doing superconducting Josephson junction. So it's interesting, anyways.
No, it
is.
Thank
you. Sorry.
So just a comment there. The transmon, and even the regular Josephson junction qubits, right? There was a paper this week, I think, where the Google group said they produced the toric code out of the Sycamore supercomputer. So it's going the other way around. So you're producing topological order from the regular qubits instead of using topological qubits.
Exactly. I mean, you can mimic anything with those guys.
Yes.
So let's make him talk.
Oh yeah, you're going to produce maybe you're going to produce a Majorana on a regular quantum computer. That's
exactly.
Yeah.
All right.
I have a question that is more or less on the lines of what Sergio said. I found it odd that all these 4 terms have the same strength, but you mentioned already that you are decreasing the number of parameters, right?
Yes. Yeah.
But did you do a study? Maybe I assume that is very hard to do, making the strengths of each one different, and then trying to check if there is a minimum number of terms that you need, like making these last 3 close to 0 and see if you still can get something, so you can get rid. Because the main problem you have there is finding the material, right? Yeah. The more terms you have, the more complicated is going to be the material. If you can get rid of some of these guys, but I assume this is a hard.
No. Yeah, hard. Maybe Rafael is still there in the chat. Can you? Okay.
Yes.
Can we reduce the number of parameters? Rafael has been playing around with this.
Okay.
And he's more up to date in the literature. But I think you can. But getting rid of the 3 body is hard.
Yeah, because all of them are 3 body, right?
Well, the first one is 2 body, like the green one.
The green one is. So, oh yeah.
Okay. The first 2 are 2 body, like you evolve 4 fermionic operators. That the bottom two, the red and the blue, they are three bodies. So you have 6 fermionic operators.
Okay.
So yeah. So yeah.
Maybe cold atoms, Luis.
Maybe cold atoms.
Cold atoms. Yeah.
Yeah. Some sort of fresh 3-body flashback resonance.
Yes. Oh, they can connect anything with anything. I mean, it's really amazing.
Yeah.
Luis,
but they are better than double layer graphene.
Oh, no doubt.
I have a question here.
Sure.
Can I ask a question?
Sure.
So Luis, thank you. Luis, can you do this with Z3 instead of Z4?
That's what we're trying. That's another thing that Rafael always been working on. Is much harder because
really? It looks like it might be easier.
I think the thing is that now you need to have, say, very strong U and get only 3 states per site, essentially. For
right,
something
like a
that.
TJ
like
model.
a TJ. Like exactly like a TJ model. So yeah, I think that's the route we're going now. But even numerically is much harder to distinguish the phases.
Ah, I see.
Oh,
so you don't know if there is a topological phase in this case.
It's not obvious that
okay.
The mapping here, the mapping is exact to the Potts model, right? So if you take this and you take delta equals, if you take delta equal W equal T, you map exactly into the symmetric Potts model. In that Z3 is not as straightforward. So it is an approximation. But so that's the thing. So Z4 is an integer number of Majoranas is doable. 2, 4, 6. Because 3 is
okay.
I think we're trying. Hopefully we'll get there.
Okay, maybe we can talk about it later.
Sure.
Thank you.
Yeah, Rafael says that Calzone and alpha, that you can create all these 2 and 3 body interactions to 2 body interactions. The problem is that the parafermions start to spread. I'm not quite sure on the convergence. So they are not localized modes like Kitaev anymore. So Rafael, if you can comment on the Z3 as well, then maybe. So.
He's typing, it seems, yeah.
Some strange interactions. Okay. Yeah,
even more strange.
Yeah. So yeah, the thing is that now we're looking, to use a quantum dot there too, but then it's definitely it's not even so clear how you can couple the quantum dot, which is all electron, to this Z3. So.
Okay, thank you.
Can I have another question?
Another question?
Okay, cool. Very quick question. Luis, do you think how this discussion on the question about Majorana, detection of Majorana, do you think this makes our quantum dot proposal even more attractive shotgun to hunt with Majorana?
Yeah. Yes, I think so. I think it would be robust against disorder. That's the thing. See, because disorder, you would have the fluctuations in the quantum dot conduction close to 1 or something, but to get to half, I don't know. That would be
but I still think the robustness against changing the quantum dot occupation is pretty attractive, I guess.
Yeah, it would be nice to have the experiments made. They actually, quantum dots for them is a problem because it creates all these extra charge, and can present. But I think that I would say that the threshold for Majoranas in nanowires has gone up tremendously. For the discovery threshold, that they can claim. Like in the retraction paper, they even say all experiments done before have to be put into question. So
let me ask something. If I understood Edson's question, what he meant to say is that the Majorana may still be there. It's just that it's another way. Instead of conductance, you are proposing another way of spotting it. But what I understood from what you said, that the comment that Dasarma made is that the Kitaev chain was destroyed by the disorder. So I don't understand. That?
The thing is that let me put in this, is that you have too many zero bias peaks to make sure that all of them are Majoranas or all of them are you really don't know. Like here, all these black dots are zero bias peaks.
Okay.
Now, what you have to have some sort of protocol to distinguish which of these can be Majoranas, or they can be quasi-Majoranas, or they can be what's the term, sticky Andreev bound states, that they cross, and instead of just anti-cross, they stick together and then they start interacting. So probably some of these dots are Majoranas. The thing is that you cannot know, right?
Okay.
I mean, the Spaniards made, right, that you have these sticky Andreev states, that they're not the true Majorana. They're protected enough that you can do quantum computation. So it will become a matter of what do you want to label them. But I mean, ultimate question is, Luis, since you went to the March meeting, so what's the next? Since just the wire alone is not enough, so you need to do braiding, but braiding is not trivial either. What are they proposing to do next?
So I think last week came out a paper. Actually, Rafael talked about that in our group meeting. From the Microsoft Q, the people in Santa Barbara, some people in Copenhagen, they published a huge paper talking about protocols, right? How many measures in parameters you have to do, do non-local, no local conductance, and everything has to be analyzed, and a huge thing. I think that's the first step, right? Is increasing data analysis, increase data and data analysis. That's the way out for the nanowires before you get the materials right. So, but what you said, that Elsa Prada also gave a talk at the March meeting, and he gave, I think, other talks where she mentioned about these quasi-Majoranas, which they can still be used, right? It's like, you might have two Majoranas on the same side of the wire, but only one of them is coupled. The other is just sitting there. And you might use this one that is coupled as the Majoranas that you produce the braiding. You couldn't do that, right? So, yeah, for me, it's hard to know. One thing that became clear from Cohen-Hoven's talk and others is that these people are in damage control mode. They have to revisit their data and try to analyze it and do different things. Non-local conductance, I think, is going to be a must, right? So a three terminal thing, you measure, you change the gate voltage here and measure there to see if what was the effect. And I think that's, for instance, a much harder experiment than the 2-point probe. So yeah.
Yeah. You got to measure what happens at both of them. They say.
Yes.
So, and that's a lot tougher. That's a lot tougher. Oh well. Thank you very much.
Okay. Thank you.
Thank you. Nancy says thank you also.
Thank you.
Thank you, Luis.
Okay, guys, we're going to go have dinner. It's really late here.
Thank you very much.
Thank you.
All right. Bye, guys. Good seeing you.
See you. George, next week you have another talk, so.
Yeah, someone
make a advertisement.
Someone asked
Too late, I guess.
Yeah, it's a bit late, but let me check here. I think it's weekend talk.
Yeah, from Catholic University.
Just a second.
All right, guys.
All right, Luis. Thank you very much.
Thank you. Very nice.
Let's keep reading the thesis.
Okay. Yeah, Lucas was here, so he's.
I have a bunch of questions for him already.
Okay, great.
I'll not anticipate them.
All right, great. Tomorrow. All right, see you.
Yeah. See you.
Bye. Bye.
Well, most people left already.
All right.
So, that's fine. Quando que você acredita que a página vai estar